Hi class. Today we meet again, and today we go into the second lesson. It is the first law of the thermodynamics. Last week you already learned some basic concepts related to the thermodynamics subject. So this week we go into the first lesson. This is about the thermodynamics, the first law of thermodynamics. And in this lesson, there will be 5 parts in the lessons. The first one is the first law of thermodynamics for a closed system. Last week you know about what is the closed system already. The second, it is the energy, a property of the system. Again, last week you familiar with the concept of the property, but last week we learned that the temperature, the pressure, volume, specific volume, etc. that is the property of the state. But the energy, you see the difference, because it is not the property of the state, but it is the property of the system. And number 3, the different forms of the stored energy. And then we move to the 4th part. That is the first law of thermodynamics applied for the flow processes. And the last part, we give some example of the steady flow processes. Okay, what is the first law of the thermodynamics? We can say this is one of the very basic and one of the most important laws for the thermodynamics. And it's based on the law of the conservation of energy. You learn about the law of the conservation of energy at the very long time, at the physics grade 6 or the grade 11. You learn this law, and it's very important. And so the first law of thermodynamics is just a version of this law. As you know, the law of the conservation of energy saying that the total energy of an isolated system is the constant. Energy can be transformed from one form to another, but it cannot be created or destroyed. Okay, so it means that the energy is conserved. It cannot be destroyed, it cannot be created, but it's just transferred from one form to another. So that is about the law of the conservation of energy. And it's applied this one in the thermodynamics, and we got the first law of thermodynamics. Now, the law for the closed system. Last week, you learned about the closed system, and here's the closed system. And you know the inside, we got the system, and outside we call the surrounding, and the barrier to separate between the system and surrounding, we call it a boundary. Okay, so normally in the closed system we don't have the materials or the mass transfer from the system to the surrounding. Only heat and work it be transferred. Okay, and you know, heat and work are the 2 forms of energy very important in the thermodynamics. And an example, the motorbike or the air conditioner, last week we already talked about that, and you know that it's kind of heat and work. And so in this case, the closed system, we only have the heat and work interact with the surrounding in the process. And last week we also know that if the system receives the heat, when we use capital Q to represent the heat, and W to represent the work. And we already know that when the system receives the heat, for example, in in this picture, we see that the Q is going into the system. So it will receive the Q. Q will have the positive, in that case, W, that is the work produced from the system. And in that case, W is have the positive value. And based on the first law, or the law of the conservation energy, one kind of the form is energy input will be equal to energy output plus the stored energy. So this one is the law of the conservation of energy. So this one we can say is the formula of the law of the conservation of energy. It's saying that the energy input equal to energy output and plus the stored energy, or energy output could be equal to energy input plus the stored energy. So in this case, we can say that the Q is the input and W is the output. So the rest will be the energy stored in the system. Or we can say the difference between the Q and W, it is the energy stored in the system. All right. So energy in the storage is neither be heat nor work. Okay, it means Q and W is not stored in the system, but it's just interacted or is created during the processes happen. So it means the energy stored is neither be the heat or work, and it's called the internal energy. And last week you learned what is the internal energy is. And simply the energy and the form of the energy there, we can write down like Q minus W is equal to delta E, or Q will be equal to W plus delta E. And again, Q here is the input energy, W is output energy, and delta E is the store energy. So in this case, delta E is the increase of energy of the system. All right. So in case there are many different heat input the system, and many different work it happen in the system, like this example. You can see that we got Q1, Q2, Q3, and for the work we got W1, W2, W3, W4, and maybe the heat is received, like Q2 and Q3 is heat received, and Q1 is heat released. Similarly, for the work we got W1, W2, and W4 is the W1, W4, and W3. We got W1 and W4 is the work received, and W3 and W3 and W2 is the work produced. So in case there are many different heat transfer quantities involved in the process, the first law of thermodynamics, we can write down is the Q1 plus Q2 plus Q3 equal to W1, W2, W3, W4 plus delta E. And in equation 1 and 2, it does not give the absolute value of E, but it's only the change of energy. So we can say that here we can only write delta E. Therefore, its energy is a property of the system. It's not the property of the state, like I just explained to you. Okay, so now we say more in detail for the energy as a property of a system. Consider a system with the changes with its states from 1 to 2. Last week, you know that one state will be represented by 1 point in the diagram. So point 1 here is represent for state 1, and point 2 here is represent for state 2. And then we got a change from 1 to 2 by the process path A. Okay, so when it's returned from state 2 to state 1, it goes in the path B. So the system undergoes a cycle. We got a cycle, all right? So writing the first formula for path A and path B, we got QA equal to WA plus delta EA. QB equal to WB plus delta EB. So the processes A and B together constitute a cycle for which the total of the work we call is sigma W cycle will be equal to sigma Q of the cycle. It means WA plus WB equal to QA plus QB, or QA minus WA will be equal to QB minus WB. So from equation 3, 4, and 5, we got delta EA equal to minus delta EB. So because it's based on this one, we got equation 6. Similarly, we look at the return process from 2 to 1. It not go in the path A, but now go in the path C. We have a similar equation is the delta EA will be equal to minus delta EC. So it means from equation 6 and 7, we got delta EB equal to, delta EC. So you see that the change of energy between two states of the system is the same, whatever path of the system is assigned to state 2. And the value of energy at state 1 is fixed, independent of the path in the system follow. Therefore, energy has a definite value for every state of the system. Therefore, energy is the property of the state. It means it's not depend on the path it goes through, but it will have the same amount. Now, we go in the different forms of the storage system. So there are two modes of which energy may be stored in the system. It may be stored in the macroscopic energy mode, or it can be stored in the microscopic energy mode. You know, macro is something big, and micro is something very tiny. Okay, so we call macro and the micro and the micro. So the macroscopic energy mode, including the macro energy, kinetic energy, and the potential energy. You know the kinetic energy and the potential energy of the system in the last lesson already. And consider a fluid element of the mass m having the center mass velocity is v bar. Okay, so we got the v bar here. Look at that example. We got the fluid mass go in the pipe, and we got in this one all the molecules. It's just run randomly, and it's got the velocity in the middle. We got the v bar. Okay, so the microscopic kinetic energy Ek K stands for kinetic, of the fluid element by virtue of its motion is given Ek equal to mv bar square divided by 2. This formula you familiar at the grade 10 or grade 11 in the physics subject. And if the evaluation of the fluid element from an arbitrary datum is Z, so Z here is elevation of the system, the microscopic potential energy EP, P stands for the potential by virtue of its potential position. So we got EP will be equal to m times g times z. M here is the mass of the flow, z here is the elevation, and g here is the gravity acceleration. So for the microscopic, what is the microscopic energy mode? Refer to energy stored in molecular and atomic structure of the system. So you know the macro is something big, and when we talk about the microscopic, is related to the molecule and the atom. It is a very, very tiny part of any materials. Okay, so we call it the microscopic. So which one we call molecular internal energy or internal energy, and denoted at the U. And in the last lesson, you know about the internal energy. And in an ideal gas, there are no intermolecular forces of interaction and repulsion. Then the internal energy depends only on the temperature. So U only depends on the temperature T. You learn about that. Therefore, the energy E of the system, E will be Ek plus EP. This is the macro mode, and the U is the micro mode. So in the absence of the motion and the gravity, so there's no emotion, there's no movement. In this case, Ek will be equal 0. And if no gravity, EP will be equal. So in this case, E will be equal U. That means the energy stored in the system is only in the form of the internal energy. And then when E equal U, equation 1 will become Q equal to W plus delta U. All right. So this one is the formula of the first law of the energy. So here we got from the law of the conservation, we write it down for the thermodynamics. We got W equal to Q equal to W plus delta U. So this one is the formula for the first law of thermodynamics. In the differential forms, equal 1 and 8 become delta Q equal to delta W plus dE. Look at this one, and you recognize that because the Q and W is not the state of the system. We already know that it cannot be stored in the system. So it's not the property of the system. So we only write is a delta Q and delta W, while E is the state of energy. So we write it dE in the differential form. And equation 8, we have delta Q will be equal to delta W plus dU. In this case, the W is the work, including WP dV, we call the work changing the volume. you see that this one is delta V. Delta V, that means the change of the volume. And it plus the, we call the engineer work, or we say that is the work of the shaft, that is moving the shaft in the motor, for example. And the work produced related to the electrical. In this formula, only the work changing volume PdE is present. So equation 9 and 10 will be written again. Is delta Q equal to P dV plus D dE, or delta Q equal to P dV plus D du, because we ignore the other form of the work. And in the integral form, we write Q equal to P dV plus E, and the same with the other question. For the pure substance, we got the Q equal to delta EK, is it kinetic energy, then the EP is the potential energy, plus delta U is the change of the internal energy, and plus work. So we got equation 11. This one is the formula of the first law of energy in for the pure substance. In other words, all this form is a different forms of the first law of thermodynamics in the differential forms or in the integral form, or we write it for the pure substance. That's just a different form. Alright, so now we go to the concept of the control volume. So what is the control volume is? When we just talk about the thermodynamics, the first law for a closed system. So in case we got the mass transfer across the system boundary, in that case, how we write the first law of the energy. Or in other words, this formula, we write it for the closed system. And one example of a closed system, as the previous lesson you already learned, that is about the air conditioner. Okay, so now for the open system, like the motorbike, we got the open system. So now we're going to write the formula of the first law of the thermodynamics for the open system like a motorbike. That means in case we got a mass transfer in and out the system. So it means we got the mass transfer across the system boundary because open system. So in this case, equation 15 we just have in the previous slide refer to the system having a particular mass of the substance, which is free to move from place to place. Consider a steam turbine like the figure here show you. Attention is focused on the certain fixed region in space called the control volume. Alright, so we got the spotlight here. It just show you that is the control volume. Alright, through which the moving of substance flows. That means we got the substance go in, and the substance go in, or the mass is go in, and the mass go out. So in this case, we got the open system. And of course, this one is, we got the boundary. The broken line in the figure represents for the control surface, okay? So the broken line here, that is the control surface. This is the same as the system boundary of the open system. And section 1 here and section 2 here allow mass transfer to take place. All right. That is about the open volume. And now, what is the steady flow processes? If the rate of the flow of energy and mass through the control surface changes with time, the energy and mass within the control volume also would change with time. Steady flow. What is steady flow? Steady flow means the rate of the flow of energy and the mass through the control surface are constant. Okay, so steady here, that means the constant. All right. In this case, the control volume in course of time attain a steady state. So at the steady state of a system, any thermodynamic property will have the fixed value at the particular location and will not be changed with time. So the steady state means the state is steady or invariant with time. That means it's not changed with time. All right? Okay, look at this picture. So this one is an example of a steady flow device. We got the flow in at section 1.1 and flow out at section 2.2. Okay, and here is the shaft, and the work is produced in the shaft. Here we got the shaft work. And A1 and A2 is a cross section of the stream. We got A1 here, we got A2 here. W1 and W2 is a mass of flow go in. W1 is a mass flow in, and W2 is mass flow out. P1 and P2 is the absolute pressure at the 1 and 2 respectively, and V small 1 and V small 2 is the specific volume, and you know this in the first lesson. And U1 and U2 again is the specific internal energy. It's the energy of 1 kilogram of the mass. V1, V2 is the velocity. Z1, Z2 is the elevation above budgetary datum. So we got the datum here, and the Z here is the elevation. So Z1 is the elevation at the flowing section, or section 1.1, and Z2 is the flowing section, elevation out of flow out section, or section 2.2. And delta Q over d tau is the net rate of the heat transfer through the control surface. And delta Wx divided to T tau is the net rate of the work transfer through the control surface. So in the steady flow, we got the mass balance, or based on the conservation law of the mass, it is no accumulation of mass in the control volume, and the mass flow rate entering must equal to the mass flow out. That means there's no accumulation or no mass stored in the system, so the mass flow in must be equal to mass flow out. So we got W1 plus equal to W2, or A1 V1 divided by V small 1 equal to A1 V2 divided by V small 2. And as you know, A here is the cross area, V is velocity, and V small is the specific volume. And this equation we know as is the equation of continuity. That is the mass balance. For the energy, we also have the energy balance. In the process, the work transfer may be in two times, the external work and the flow work. For external work, Wx refers to all the work transfer across the control surface other than that due to the normal flow forces. In engineering thermodynamics, the only kind of the external work is important are the shear work, or we call the shaft work. I mean, we already know that the work is turning the shaft of the motor around, and the electrical work. For the flow, the workflow is a displacement work done by the fluid of mass dm1 at the inlet section 1 and that of the mass dm2 at the exit section. So we got here is the displacement work, or the work changing the volume. We got the because it's the entering, so we got the minus P1 V1 time dm1, and the outside is a positive. We got a positive P2 V2 dm2. So total of work, we got the W will be the external work Wx, and the flow work will be this one, two elements here, and in have the negative and out have the positive. In the rate form, we rewrite this formula in the form of the ratio. We got this formula and this formula. So since there is no accumulation of energy, by the conservation law of the energy, the total rate of the flow of energy stream entering the control volume must equal to total rate of the flow of all energy stream leaving the control. It is expressed by the equation. So all the entering in equal to all energy out, because in this case there is no energy stored in the system. In this formula, E1 is specific energy, W1 is the mass of the float in, delta Q divided to D tau equal to, that means the energy entering we got in terms of the heat Q, and the energy out we got the energy in terms of the work W, and E1 E2, that is energy stored in the system, as you know when we talk about the energy in the closed system. So substitute delta W to d tau from the equation 16. We got formula, or we can write down, and we got the equation 17. So in this case, you see this one energy stored in the inside. That is the displacement work. That is the heat entering the system. Again, energy stored and outside. This is displacement work, and this is the work produced in the system. And E1 and E2 refer to energy carrying into and out of the control volume with the unit mass of the fluid. And the specific heat E is given by the E equal to the kinetic energy, potential energy, and the internal energy. And for the kinetic, because we write this formula for 1 kilogram, so we got the EK, you know, that is equal to V squared divided 2. For the potential, is the Z is the elevation, and the G here is the gravitation acceleration, and U is the internal energy. So substitute expression for E into equation 17. We have this formula. Okay, so here we we replace E by this one. So the input we got is V1, Z1, U1, and the output we got the V2, Z2, and U2. All right. So we can say this is the formula of the first law of the energy written for a steady flow process. As you know in the previous lesson, that means that we say H here is enthalpy. The enthalpy will be equal to U plus PV. In this formula, we got U is the internal, P is the absolute pressure, V is the specific volume, and enthalpy H will be equal to U plus PV. So we replace this one into equation 18. So the equation 18 become this formula. So you see the same, but because we got the U plus PV equal to H, so the formula will be written again in this form. And in the equation for continuity, we got W1 equal to W2, or we let W equal to dm divided by d tau. And divide this equation 19 by dm to d tau, we got this formula. So this equation 19 and 20 are known as the steady flow energy equation to control volume. All the terms in the 19 equation represent energy flow of the unit mass per fluid, whereas all terms in the equation 20 represent energy flow per unit time. So the difference between this form and this form, it just you see in the equation 19 we got the tau here related to the time, but in 20 we got the m here is related to the mass. And equation 20 can be rewritten as this formula. All right, that is about the first law of energy for the steady flow. And now we go into some example. Or in other words, we use the first law of energy to write the formula for different cases in steady flow. So in the differential form, the steady flow of energy equation becomes this form, is delta Q minus delta Wx equal to dH plus V bar dV bar plus G dZ. So here is the entropy. Because the flow, the energy will be represented by the entropy. This one is related to the kinetic energy. V here is average velocity, and G dZ here is related to the kinetic. In this case, you know, G is the gravitation acceleration, and Z here is elevation. Okay, so we apply the first law of energy, the first law of thermodynamics for the nose and the diffuser. So what is the nose? A nose is a device which increases the velocity of the kinetic energy of a fluid at the expense of its pressure drop. Or in other words, when the flow go into the nose, it will reduce or the pressure will drop, and the energy will be transferred in the form of kinetic, and it will increase the velocity. So we call that the nose. Whereas a diffuser increases the pressure of a fluid at the expense of its kinetic. So it means if we need to increase the velocity, we use the nose, and if we need to increase the pressure, we use the diffuser. So for both nodes and the diffuser, we have the same equation of the first law of the thermodynamics as question number 20 here. You know, this one is section 1.1 and here section 2.2. And the nodes here will be insulated. So this one is represent for the insulation. Because there's no heat and no work happen in case of the nodes and the diffuser. So we got the delta Q divide dm equals 0 and delta Wx divide dm equals 0. And the change of the potential energy is 0. So the equation 20 will be reduced to very simple equation. It's V1 square divide 2 plus H1 equal to V2 squared 2 plus H2. In this case, you know that the V here is the velocity at the input section. H1 is the enthalpy at the input section. And similarly, V2 and H2, that is the velocity and the enthalpy at the output section. And the continuity equation gives W will be equal to A1 V1 V small 1 and equal to A2 V2 V small 1. When the inlet velocity, or we call the velocity of approach V1, at very small compared to the V2. So this above equation become, because in V1 is very small, so we just ignore it, and we got the H1 equal to V2 squared divide 2 plus H2. So in that case, we can calculate the velocity at the output section is the V2 equal to 2H1 squared. And this equation can be applied for the diffuser as well. The second example, we do it for the throttling device. For example, the valve, we normally in the system we got the valve, right? So the valve here is one example of the throttling device. So when the fluid flows through a constricted path, like a partially open valve or an orifice or the porous blood, there is a pressure drop of the pressure and the flow is set to be throttled. Same at case of the nodes and the diffuser, the steady flow of the system equation, we will call that equation is SFEE. It's a steady flow energy equation. For the throttling device, will be reduced to the same formula for the nodes and the diffuser. Often the price velocity in the throttle are so low that a kinetic term is negligible. So it means we can ignore this V1 squared divide 2 and V2 squared divide 2. So in that case, we got H1 equal H2. So it means for the throttling device, the enthalpy of the fluid before throttling is equal to the enthalpy of the fluid after throttling. So that is for the throttling the device. And another example, the turbine and the compressor. The turbines and the engine give positive power output, whereas the compressor and the pumps require power input. That means it have the negative value. That is different between the turbines and the compressor and the engine compared to the pump. For the turbine, which is well insulated, the flow velocity are often small, and the kinetic energy terms can be neglected. So the steady flow energy equation then become, again, we ignore the term of the kinetic. So we got the H1 equal to H2 plus the delta Wx divided to dm. So in this case, we only have the enthalpy and the work produced in the turbine. So in this one, we can rewrite, we got formula Wx divided m equal to H1 minus H2. So the work is done by the fluid at the span of its enthalpy. Or in other words, they will reduce enthalpy to produce work in the turbine. Similarly, for an adiabatic pump, we say the adiabatic, it means isolated. For the pump and compressor, the work is done of the fluid, and the W, W is negative. So in this case, we got the H1 equal to H2 minus Wx divided m. So Wx minus will be equal to H2 minus H1. So it means the enthalpy of the fluid increased by the amount of the work input. So this one is an example of the picture for the flow go through the turbine. The last example is the heat exchanger. So the heat exchanger is the device in which heat is transferred from one fluid to another. Okay, so the following figure shows a steam condenser where the steam condenses outside the tube and the cooling water flows through the tubes. So we got the steam here. For example, later on when you learn about the refrigeration system, we will have the condenser. So the condenser, or we call in this case a steam condenser, is the same. So we got the exhaust steam go in kind of steam or the vapor, and after that, when it's released heat to the water flow in the system here, it releases the heat to the water and it will be condensed. It becomes the condensate. So of course the cooling water in will be the cooled water, and after it receives the heat from the steam, it becomes hot and it's become the steam, the hot water out. So the steady flow energy equation written for the steam condenser, you got this formula. You got a formula Wc H1 plus Ws H2 equal to Wc H3 plus Ws H4. So you know that Wc is the mass of the water, cooling water go in and go out, whereas Ws is the mass of the steam go in and go out. And of course, H1 is the enthalpy at the input of the water. H2 is the enthalpy of the steam input the system. H3 is the enthalpy of the living water, and H4 is the enthalpy of the condensate leaving the condenser. Here, the kinetic and the potential terms are considered small. So there is no external work done, and the heat exchange is the form of the heat is confined only between the two fluids. It means there is no external heat interact or the heat loss. So we got the Ws time H2 minus H4 equal to Wc H3 minus H1. All right. So this is about the apply of the first law of the thermodynamics for the steady flow. Different example. All right, so that is the end of the lesson, the first law of the thermodynamics, and I already uploaded the materials in your BKE learning, and please read it and do the exercise in this chapter. As you know that for the engineering subject, when you do the exam or the test, mostly you just do you solve the problems, not the theory. So do all the exercise in the chapter I provided to you. Same in the first lesson, even that is the first lesson, but as you see in the materials I uploaded, you can see a lot of exercise and the problems in the end of the chapter. So please do it at home. And again, if you got any questions, feel free to contact me through the email and or the phone. So thank you for listening, and good luck and goodbye.